All right. Are you ready? All right, today we're going to talk about basic switching regulators. The difference between a switching regulator and a linear voltage regulator is basically that the transistor got two conditions. It's on or it's completely off. That means the transistor works as a switch, and that makes the efficiency of the switching regulators much higher than of the linear series regulators. First of all, we're going to talk about the step-down switching regulator. In the case of the step-down switching regulator, here's the basic, very practical circuit diagram. Not practical, but just to illustrate that, we use the transistor or the control element as a switch. That means it's going to be on or it's going to be off. And then we got a LC filter to filter the output of the regulator. Now, not very practical to do it by means of a switch, because then the whole time you're going to use the switch. Not very practical, but that's only for explanational purposes. The next one, here's the basic step-down switching regulator. What you got here, we got a reference voltage, again a resistor and a zener diode. We got our comparator that's going to sense the output, where we got a voltage divider or sampling circuit, and then we got a variable pulse width modulator that's going to vary our pulse width depending on my error signal coming from the comparator, and here is my LC circuit. The diode there is just to protect my transistor there, and that's the purpose of the diode. Let's go and quickly have a look how this thing is operating, depending on the on time and the off time. If we look at this, depending on the on time and the off time, the longer the on time, the higher the output voltage. The smaller the on time, the lower the output voltage. Now here you can see here's the filter action of my LC filter, and there is my output voltage depending on this on time. The period is from there to there. There's the on time and there's the off time. If I increase my on time, my output voltage will also increase. That means I increase the on time and decrease the off time, I will have a high output voltage. If you look at the last one here, I got a very small on time and a much larger off time, and then the output voltage will also decrease. A few formulas that's important here. V out is equal to T on divided by T, where T is my period and T on is my on time times my input voltage. The period is equal to 1 upon F, and my period is also equal to my on time plus my off time. That is for the step down switching regulator. The next one we're going to talk about is my step up configuration. All right, this figure B here is still for the basic action of the step down switching regulator. It only shows us if my output attempts to decrease, what will happen. If the output voltage decreases, what's going to happen? If the output voltage decreases, the voltage here of the sampling circuit there will also decrease. All right, and that will tell the variable pulse width modulator to increase. That means I will increase the pulse width. That means I will also increase the output. These variations is normally quite small. That is when there's small variations at the output. The next one, when V out attempts to increase, that means my output voltage tends to, if I do certain things at my load, when the output voltage increase, the voltage at this point is also going to increase. When that increases, it will tell my pulse, my variable pulse width modulator to decrease the on time. When I decrease the on time, I will also decrease my output voltage. Again, I repeat, that is normally small variations. The next circuit is basically my step up switching regulator. that means the output voltage will be larger than my input voltage. All right, that's a step up switching regulator. You will notice that this MOSFET is now connected in parallel with my output, not in series. I will have the coil in series. Now, before we going to look at the operation of this circuit, we must know what happens in a coil. If I take a coil and a resistor and a battery and put them in series with a switch, and when I close the switch, what will happen? We must remember, when I close the switch, the voltage will be maximum across the coil and the current will be a minimum. The current will increase to a maximum 5 time constants and the voltage will decrease to 0 in 5 time constants. That is very important to know. But let's go and look at our circuit there. If you look at this circuit diagram, here we show the transistor goes from off to on. When it goes from off to on, my voltage across my inductor or my coil will increase, will be maximum. As I keep it on, the voltage will decrease. You can see the voltage decreases, all right. And when that happens, we will notice, what can I say about the diode? The diode's going to be basically reverse bias because I will have a negative voltage on the anode and a positive voltage on the cathode, right? Now, when my transistor goes from on to off, what will happen? The following will happen. The magnetic flux will collapse and it will generate an EMF with the opposite polarity. Now you'll notice the voltage will now be negative positive because the flux collapses, generate the EMF with the opposite polarity. Now it will be positive, negative, positive. The diode will be forward biased and now I will charge the capacitive positive, negative, and my output voltage will be V in plus VL. That means the output voltage will be much larger than the input voltage. That's why we call it a step up switching regulator. The next one is the voltage inverter configuration. In the case of the voltage inverter configuration, you will notice that the control element in this case is now going to be in series and I will have my coil. What's going to happen? When my transistor turns on, what happens? Goes from off to on. The voltage across the coil will be positive, negative, it will be maximum, and as I keep it on, it will start decreasing. The diode now is going to be reverse biased because I will have positive there and I will have negative there. Diode is reverse biased. There is no flow there. When the transistor turns off, what happens then? Again, the magnetic flux collapses and generates the EMF with the opposite polarity. Now it will become negative positive. You can see it shoot down, maximum negative, and then it will start decreasing. Now the diode is forward biased and we will charge a capacitor positive, negative because the diode is forward biased. My output voltage will be a negative voltage. That's why we call it inverting switching regulator. The next two figures, they just show us if there's a change in output, how do we correct that change in output. All right. The same as the previous one from the sampling circuit, and it's going to basically just rectify that small variation in the output. And now the 17.5 integrated circuit voltage regulators. These are linear voltage regulators. What we have to know, we've got a 3-pin linear voltage regulator. It's a 7-8 series from a 7805 to a 7824. The last two digits indicate the supply voltage. The 78 indicates it's a positive voltage regulator. For example, a 7805 is a plus 5 volt. A 7815 is a 15 volt. A 7824 is a 24 volt regulator. It's a 3-pin regulator where input, the ground, and the output. One thing important, normally we have to secure them to a heatsink. to prevent thermal overload. What they say, the 7/8 series can produce output currents up to in the excess of 1 amp when used with an adequate heatsink. The input voltage must be approximately 2.5 volts above the output voltage in order to maintain regulation. Very important, my input voltage should be at least 2.5 volts higher than the output. If that's not the case, we won't get regulation. The circuit have internal thermal overload protection and short circuit current limiting features. Thermal overload occurs when the internal power dissipation becomes excessive and the temperature of the device exceeds a certain value. Almost all applications of regulators require that the device be secured to a heatsink to prevent thermal overload. If you're going to draw very small amounts of current, then it's not necessary, but if you're going to draw in the excess of 500 milliamps or that, you should secure it to a heatsink. And also depending on the difference between the input and the output, because that will also increase my power dissipation of the control element. The next one, fixed negative linear voltage regulators. Now our negative voltage regulators are the 7/9 series and 7905 or 7924. That is negative voltage regulators. Important to know, the input voltage must be negative, and if you use electrolytic capacitors, make sure that should be the negative terminal and that should be the positive terminal. Otherwise, you will basically blow up those electrolytic capacitors. All right. Then we got adjustable positive linear voltage regulators. Their outputs being adjusted. If you look at the first ones there, that must be connected to ground. This adjustable regulators, that is not going to be connected to ground. The adjustment terminal. One very important thing, the reference voltage in this case, in the case of the LM317, is 1.25 volts. It's a standard value, 1.25 volts, all right? Let's quickly go and have a look. If I move the slider of R2 to the top position, I actually make sure R2 is 0. That means then it's been connected to my ground reference. Then the output voltage will be the volt drop across R1, and that will be 1.25 volts. If I move it to the bottom position, I will have that volt drop plus that volt drop. That means then I will have maximum output voltage. Here they tell us I reference is V reference divided by R1. The reference voltage, as already mentioned, is 1.25 volts, and that is a fixed value. It's a standard value. All right. And here they say the output voltage can vary from around about 1.2 volts up to 37 volts. Again, the input voltage must always be higher than the output. That means if you want to, for example, have a 37 volts output, you should at least have around about 40 volts at the input of this adjustable linear voltage regulator. If you look at this circuit diagram, figure 17.29, you will find there's my adjustable terminal. We will have adjustment terminal current of around about 50 microamps. That means the current that's going to flow there, I adjust, it's around about 50 microamps. Again, I repeat, the reference voltage is 1.25 volts. Now we're going to have a look at the output. We can say that the output is equal to VR1 plus VR2 because that will be my output voltage. Then I can say that VR1 is I reference times R1, and the voltage drop across R2 is equal to I reference times R2 plus I adjust times R2. All right. When we simplify, we'll get VR is equal to V reference bracket 1 plus R2 divided by R1 plus I adjust times R2. All right. Let's have a look at this example. Example 17.6. If you look at the example 17.6, they say determine the minimum and maximum output voltages for the voltage regulator in figure 17.3. Assume I adjust equal to 50 microamps. First of all, If I move the slider to the top position, I know the resistance value of R2 is 0. And then I can say VR1 is equal to V reference 1.25 volts. If I put it into this equation, I will also get 1.25 volts because that will only be the volt drop across R1. When I set R2 to the maximum value, that will be 5 kilo ohms. Then I can work out my output. It's V reference 1 plus R2 divided by R1 plus I adjust times R2, and it's equal to 1.25 volts bracket 1 plus 5 kilo ohm divided by 220 ohms plus my 50 microamps times the 5 kilo ohms, and that will give me 29.9 volts. That means I can adjust from 1.25 volts to 29.9 volts. Then we also get a negative voltage regulator. The negative voltage regulator is a LM337, exactly the same story, but now please take note, I will have a negative input voltage that will also give me a negative output voltage. This reference voltage is again going to be minus 1.25 volts, also 1.25 volts there, and that is my negative voltage regulator. That brings us to 17.6, integrated circuit voltage regulator configurations. Here we are again going to use a 7/8 series linear voltage regulator. But we know, for example, this regulator can only handle, for example, 1 amp maximum. Now, if we want to handle much larger current, we can put a pass transistor there or this external transistor to increase my current. Here they state R external is equal to 0.7 volts divided by I maximum. Now, if you look at this circuit here, if my current, if the volt drop across this R external is smaller than 0.7 volts, this transistor will be off and all the current will flow through the voltage regulator. If that voltage drop becomes larger than 0.7 volts, I will turn on this transistor. This certain amount of current will flow through there, and the rest of the current will flow through my pass transistor or my external transistor. Then we can also bring in current limiting into the circuit. If we want to limit the current that's going to flow through this external transistor, we can bring in this current limiting circuit. Circuit, let's assume that volt drop across this resistor there is less than 0.7. There will be a certain amount of current flowing through there because that is larger than 0.7, and that transistor will be on and there will be current flow through that transistor as well. But the moment that volt drop become larger than 0.7 or 0.7 volt or larger, what will happen? I will start doing the current limiting, and this current can't increase anymore due to the current limiting circuit here. A current regulator. If I look at the following circuit here, figure 17.38, let's say we use a 7805 linear voltage regulator. We know that the voltage between that point and that point is going to be 5 volts. That's due to the regulating action. Now put a certain resistor there, I will have a constant current that's going to flow there. If I even put a short circuit there, the same current will flow through there. Alright, there will be a small adjustable current, but that can be basically neglected. Let's have a look at this example. They say, what value of R1 is necessary in a 7805 regulator to provide a constant current of 0.5 amp to a variable load that can be adjusted from 1 to 10 ohms? You can't make this too large. If you make it too large, you won't be able to have a constant current there, or you make it too high. Now they say the 78 produce 5 volts between the ground terminal and the output terminal. Therefore, if you want 0.5 amp of current, setting resistor must be neglecting IG. then I say R1 is VR divided by IL, and that'll give me a 10 ohm. If I put a 10 ohm there and there's 5 volts across there, it will give me 500 milliamps, all right, or 0.5 amps. Now, if I put a short circuit there, there will be 0.5 amps flowing. If I increase that resistor, there will still be 0.5 amps flowing there. If you make it too large, then it won't be able to keep at a constant current. That's the end of the story.